If you ever put some on your skin, what does it feel like? It feels cold because it starts evaporating immediately. Acetone, if you leave the cap off that, it's going to evaporate very fast because it doesn't have the intermolecular attractions between molecules like water does. So there's nothing holding it there. Not as much holding it there. Won't say nothing. Okay, so vapor pressure, like Quanell was saying, is these molecules that are hitting the surface and going off, turning to vapor, create pressure. Because that's what pressure is gas molecules striking the surface of their container. So there's pressure from there, coming off the liquid. Vapor pressure. Now, if we have a solute in the solution, say we got sodium chloride dissolved in here, and we've got these ions floating around, and they're in the way. Okay? If we have a solute, then the vapor pressure will go down, because it's likely that if we have this water molecule that is heading towards the surface with enough energy to break apart the hydrogen bonds and go off as a gas, it might run into a molecule or an ion of the solvent and be deflected back down into the solution. They're just in the way. They make it more difficult to change phase. So the vapor pressure will go down. Okay, vapor pressure lowering. Raoult's law. We've got, let's start on this side. P naught is the vapor pressure of the pure solvent. That's before we add solute. What's the vapor pressure of our solvent? X is the mole fraction of the solvent. Okay, what part of the solution is solvent by moles? And then P1, that will be the new lowered vapor pressure because of the solute. All right, which one of those on our little sheet is a vapor pressure problem? Number 2. 2. The vapor pressure of water at 20 degrees Celsius is 17.5 torr. Okay, is that P1 or P naught?
P naught.
That's P naught.
Why are you calling it P naught?
Not.
That's what that means?
Yeah. Is that what y'all called it in physics? I know not. P naught. 17.5 torr is P naught. What else are we given? What is the vapor pressure of water over a solution containing 300 grams of C6H12O6, and we've got 455 grams of water. Okay? So we know this. All we need is to find the mole fraction of the solvent. How are we going to find the mole fraction of the solvent? Brenda? I think we're going to have to do some calculations. Well, we want a mole fraction, and we're given grams, so what do you suppose the first thing we're going to have to do with it? Huh? No, there's no volume here. Not molality. We just need to know the fraction by moles that is water. So we got to convert to moles. So we got 300 grams of glucose and 455 grams of water. Let's convert them to moles. 1 mole of C6H12O6 is what? 180 grams. And 1 mole of water is 18 grams. Okay, take your chubby fingers and stab at your calculators for me. 1.67 moles of glucose. How many moles of water? Okay. Do we want the mole fraction that is glucose or the mole fraction that is water?
Glucose.
And later, do we want the mole fraction that is glucose or do we want the mole fraction that is water? X is the mole fraction of the solvent. What's our solvent? Water. Then we want the mole fraction that is water. So basically, fraction is like a percentage, but we don't multiply by 100. We leave it in decimal form. So our fraction that is water is 25.3 moles divided by the total number of moles. So 25.3 moles plus 1.67 moles. So our mole fraction should be like 90-something%. What do you get? What? It better be 90-something. What? Yeah, 0.938. Okay, that's the mole fraction that is water. So we got our X. Huh? This will be mole fraction. Okay? So now let's plug it into our Raoult's law formula. P1, the pressure after adding the solute, is going to equal the mole fraction, which is 0.938 times the pressure it should lower it a little bit. What is it? 16.44. So it lowered the vapor pressure slightly by adding the solute. And it didn't matter what the solute was, it only mattered how many particles we had. Any questions?
So when we do, we always look for the
When we do, we have to look for the what? We gotta have the mole fraction, yes. So the moles of the solvent divided by the total moles.
And so the solvent will always be water.
No, all it does now is have to be water. You can have things dissolved in other substances. Any other questions?
Solvent always goes on.
What?
Solvent always goes on top of the.
Yes, because we want the mole fraction of the solvent.
Down the bottom, you add both of them.
At the bottom is total moles. All right, what's the next slide? 27. Boiling point elevation. Okay, just like we were talking about having a solute in a solvent lowers the vapor pressure, it also makes it hard for that solvent to boil. So it's going to take a higher temperature to make it boil. So we're going to, having a solute in a solvent elevates the boiling temperature. Okay? Our equation for boiling point elevation is delta T sub B, which is the change in boiling point temperature. It's going to be equal to some constant that is specific to our solvent, K, times the molality. And I'm going to add one more thing on there. Y'all see what I have here? Times I. So I'm going to write it like this. Delta T sub B equals K sub B times molality times what's called the Van Hoff factor, I. And this is acceptable. This is acceptable as long as we're dealing with a molecular solute, a covalent solute. But a lot of times our solute is not molecular, but it's ionic. And with colligative properties, it only matters the number of particles. So if we dissolve an ionic compound, we're going to get more particles. For example, if we have this C12H22O11, if that's my solute, then my Van Hoff factor is going to equal 1. This is sucrose. It's a covalent compound. For every one sucrose that I dissolve, for every one particle of sucrose, I get one particle in solution. So my Van Hoff factor is 1. So for a molecular compound, we don't really need this I, which is why it's not on the PowerPoint. But if my solute is this, sodium chloride, if I dissolve that in aqueous solution, I really get 2 particles for the price of 1. So my Van Hoff factor would equal 2. So my effective molality would be doubled because I'm getting twice as many particles. With colligative properties, it only matters the number of particles. All right, what if I have magnesium chloride is my solute? What's my Van Hoff factor going to be? 3, because I'm going to get a magnesium 2+ ion plus 2 chloride ions. My Van Hoff factor would be 3. Do I need to do another example of how to find the Van Hoff factor? What would be my Van Hoff factor for aluminum oxide? Van Hoff factor would be 5 because I'm going to get 2 aluminium 3+ ions and 3 oxide ions. So you would get 5 particles from that. So if we knew the molality of aluminium oxide, we would multiply it by 5. Our effective molality in solution would be 5 times. Okay? All right, what problem on our little worksheet is a boiling point elevation problem? Number 4. Calculate the boiling point of a solution made from 227 grams of magnesium chloride to 227 grams